mistake I made at the end of our last lecture. For this section only, I corrected it later on in my 11 a.m. session. But this one, I made a mistake when solving for the unit of A. So this one, what I told you was like the other way around. But in fact, like A need to cancel out its unit with Vm squared on the bottom. And then also remain like a bar, which is a unit of pressure there. So I made that mistake and I sent out the correction email. I updated our annotated note, and here I just want to bring your attention again, like I got that wrong and I want to correct it. All right, so, and before we move on to our today's lecture, I want to have a quick reminder. You have our syllabus quiz due today and your discussion worksheet due on Sunday night. So just to let you know, don't miss those deadlines, please, okay. All right, so back to thermodynamics. In our last lecture, we went over ideal gas law and how do we derive ideal gas law using experimental relationships like Boyle's law and Charles' law. Now, today we want to go a little bit further to make a more general statement on the equation of state, right? So last lecture, we see the ideal gas law, we see the van der Waals gas law. So effectively, all of these equation of state tells us the relationship between your volume, or in this case, molar volume, assuming we don't have any exchange of matter. So we have a molar volume, we have pressure, and then we have temperature. Like, for example, what is said is if we have a fixed molar volume and pressure, we have a way to say like temperature is also fixed. Or like say if we fix temperature, we have a way to experimentally measure or to derive the relationship between the other two properties, right? So the equation of state is an experimentally determined relationship between these macroscopic thermodynamic properties. Now, in this part, the question we're trying to answer here is how many experiments do we need to measure in order to decide the equation of state, right? So we have these three terms interconnecting with each other. Technically speaking, we have a total of 6 partial derivatives. But how many experiments do we need to determine that equation of state? Like what we see in the ideal gas law, we only have 2 sets of experiments that helped us deriving the equation of state, right? But is that generally true? And how do we mathematically derive those 2 out of the 6 partial derivatives we need? So here we're gonna use a little bit more calculus than we just showed you before. So let's get started and get an idea about how much, like this lecture will represent the maximum amount of calculus technique you will need in this class. Like if you feel comfortable about like what we're talking about now, you should be comfortable with whatever we're gonna talk about in the rest of the lecture on the math end. All right, so getting started. When we talk about the partial derivatives, again, we have 3 variables. So thinking about those 3 variables, first of all, is we can have 3 pairs of partial derivatives, meaning that we keep one of each variable as a constant, and then we write that pair of partial derivatives. So in this case, for example, we have an isothermal process. So judging by its name, whenever we say a process is isothermal, what we're saying is we're keeping the temperature as a constant. Or in the partial derivative end, we're putting the partial derivative of your molar volume over pressure at constant temperature, or partial derivative of pressure over molar volume at constant temperature. But using calculus, like the simple relationship we're using is just a partial derivative of z over x at constant y. This will equal to 1 over the partial derivative of x over z at constant y. So this pair of partial derivative is internally connected, right? So that's also making sense. If we keep the temperature at constant, then there's only one relationship describing the relationship between your molar volume and pressure. It doesn't matter whether you put the pressure or molar volume on the y-axis or the x-axis, all right? So the same apply to isobaric processes and isochorus processes. So we can reduce our 6 partial derivative into 3. But let's just go over it one by one to consolidate our understanding. Next one, talking about isobaric process. So this means whenever we say isobaric, we're saying we're keeping the pressure at constant. Right? So we see constant pressure symbol in all these partial derivatives. And again, we have 2 sets of partial derivatives, the molar volume over T or T over molar volume. Now these 2 are interconnected with each other, right? And the third one, obviously, is keeping our volume as a constant. Or we call it isochorus processes. So these are like 3 more terminologies in thermodynamics. Isothermal, constant temperature, isobaric, constant pressure, and isochorus, constant volume. So in this case, we're keeping our molar volume as a constant. This one should be Vm. And your relationship between your pressure and temperature is thus related. All right, so now starting from the 6 partial derivatives, we now have 3. We just need to have 3 experiments to measure them. Or can we take one more step to further reduce that 3 partial derivatives we have in mind? So the next step is to further use calculus to decrease the amount of partial derivatives we have to measure experimentally. And in this part, we're using the cyclic chain rule. So again, the cyclic chain rule, like what we just showed before, is a simple mathematical relationship, saying like dx over dy at constant z times dy over dz at constant x and dz over dx at constant y, product together equals to -1. So the 3 variables we have are the molar volume, pressure, and temperature. So we can rewrite the cyclic chain rule using our 3 variables. So that becomes dp over dvm over t, dvm over dt at constant p, and dt over dp at constant vm. It doesn't really matter which order you put it. The fact is, because we have the cyclic chain rule linking these 3 partial derivatives together, now we have one more relationship to reduce the amount of derivatives we have to measure, right? So we have one more relationship to use. Now, in this case, using the same relationship, the dz over dx at constant y equals to 1 over dx over dz at constant y again. So what we can do is let's focusing on just one of these terms, right? I'm randomly picking the dp over dt at constant volume. So the whole point I'm picking this one to reduce is because it's a little bit more, wait, one sec. I'm picking this one. Let's pick this one here. Because it's a little bit harder to measure your change of pressure while keeping the volume constant. But you can pick any of it. The fact is, we can pick any pair, but I just like seeing this one as, well, I just picked this quite randomly. So next one we're using is writing this out. So dp over dt at constant Vm. I'm just moving this one to the right-hand side. That equals to negative dp over dvm at constant t times dvm over dt at constant p. Right. Or using this relationship again, we can rewrite this as negative dVm over dt at constant p over dVm over dP at constant t. Just flipping this one to the bottom, that's all. All right, so effectively, what we are saying here is by measuring these two independent partial derivatives, we have a way to say or to derive the full relationship between the three variables: molar volume, pressure, and temperature. All right, so that's why we only need two experiments to derive the equation of state. So in this case, let's give them like real names like people use for these two partial derivatives. Again, we pick these two partial derivatives because measuring the volume change is slightly more straightforward when we're designing the experiment. And hence, it's easier for us to say like measuring these partial derivatives experimentally. Now, if you have like better ways to monitor the change of pressure over temperature, you can always replace one of these terms with that. All right, so there's no, like mathematically, there's no reason to say like we pick these two, but experimentally it's easier to design these experiments. So from these two partial derivatives, then scientists design these two coefficients that we can experimentally measure and then use these coefficients to go back and derive our equation of state. Right, so these two coefficients are experimentally measurables. Like the first one is called the thermal expansivity or cubic expansion coefficient. So that's 1 over Vm times this partial derivative dVm over dt at constant pressure. And the bottom is called isothermal compressibility, which is, 1 over Vm with a negative sign, and then partial derivative of Vm over dP at constant T. So one of the questions we like to ask ourselves is, what is the dimensionality of these coefficients? So we can easily derive their dimensionality, meaning what is the unit of these coefficients, by thinking about the ideal gas law. So for example, we know that PVm, molar volume, equals to RT for ideal gas. So we should be very straightforward to derive the thermal expansivity and isothermal compressibility for an ideal gas. Right, so in this case, if we're focusing on Vm, then write the volumetric ideal gas equation of state. That's Vm equals to RT over P. So for the thermal expansivity, alpha equals to 1 over Vm. So that's P over RT. We're taking the partial derivative of Vm over T. So that's taking R and P out as constant. And T just disappeared because we're taking a derivative. And in here, P and P cancel out, R and R cancel out. And we can see the unit of our thermal expansivity is 1 over T, or K minus 1. All right. And then for our isothermal compressibility, we have chi. So that equals to, negative 1 over Vm. So again, P over RT. And then we're taking the partial derivative of Vm over P. So we have RT comes out as your constant times negative 1 over P squared. So lots of things cancel out. Your RT cancel out with RT. One of the P cancel out with the P. The negative sign cancel out. So your chi, the isothermal compressibility, will have the unit of 1 over P or 1 over bar or torr or Pascal, whichever pressure unit you like. All right. So that's the easy version, which is using ideal gas law. And now we're talking about real calculus and try to solve for the more complicated situation. We're just taking one step further, but math can get nasty very, very fast. So in this example, let's look at something beyond the ideal gas. So we'll do this together, but let's think about it. Again, let's have the van der Waals law equation of state. So that's P plus A minus Vm squared. Remember, this one is adding attraction between atoms or molecules when they're in close proximity, but not too close. And then Vm minus B. So this is telling you your gas molecules are solid balls. They don't have volume. And this equals to RT. All right, and can you write an expression of our thermal compressibility, which is alpha equals to 1 over Vm times partial derivative of Vm over T at constant P. So this is where math can get nasty, and we will be using calculus techniques to solve this kind of problems. So I'll give you some time to think about it, but let's get started with 3 different approaches in solving this problem, but all of them will lead to the same answer. So I'll be working with like one of them with you in this section. I'll work on a different one in my 11 a.m. section. So if you look at the recording, you'll also get a hint from that. And the third one is too complicated and I don't want to touch it. But if you want to try it, you can also try it yourself. So let's think about it. Obviously, the most complicated one, that's the one I don't want to touch, is using the quadratic equation and actually solve for an expression of Vm from the van der Waals equation. It's very complicated, and that's why I'm trying to avoid it. But there are 2 different, more simple ways we can use calculus to help us solve this relationship. First one, now, although expression of Vm as a function of P and T is very complicated, expression pressure as a function of Vm and T is not too bad. Expressing T as a function of Vm and P is also not too bad. So we can use our cyclic chain rule, right? So our dx over dy at constant z, dy over dz at constant x, or dz over dy, this one is not, dz over dx at constant y equals to -1. So we can use our cyclic chain rule to help us, instead of solving for Vm, just expressing like pressure or temperature as a function of the other 2 and use the cyclic chain rule. Second approach is to say, now we have 2 different terms here, right? So left and right. So what if we use the relationship dxy equals to x dy plus y dx? And that's also going to help us solving this relationship. So we will be focusing on the first one here. So let's do this together. I'll be doing it on the board. If you have a piece of paper, let's just work on it together here. I'll leave this one here for you. Okay. So what do we have? Since we're using the cyclic chain rule, let's just write it out, right? So we have the partial derivative of molar volume over T at constant P, or dt over dp at constant Vn, and dp over dvn at constant T, and this equals to -1. And people in the back can see it? Okay, sounds good. So in this part, what we want is this term, right? So the partial derivative of Vm over T at constant P. But it's not straightforward to solve for Vm, so let's solve for the other two and use the cyclic chain rule later on. So let's look at this one as our first term. So we're talking about the partial derivative of T as a function of P at constant Vm. So we can rewrite that equation as a function of T. So T thus equal to 1 over R times P plus A over Vm squared Vm minus B. So in here, since we're keeping our Vm as a constant and we're taking the derivative over pressure, now this term here doesn't have any pressure dependency. So when we're taking the partial derivative of T, bless you, over P at constant Vm, this term will disappear since it doesn't have any pressure dependency. With me so far? Right, so then we can write this partial derivative as simply Vm minus B over R. And that's the only P we have in this partial derivative. Right, pretty straightforward. And then let's look at the second part. Likewise, when we're solving for that part, we want to rewrite our van der Waals equation as a function of P. So what we have is pressure now equals to RT divided by Vm minus B minus A over Vm squared. So again, we're just moving the terms. So divide both ends by Vm minus B and minus A over Vm squared to find an expression of P as a function of molar volume and temperature. And then what we want to do is taking the partial derivative of P over Vm at constant T. So in this case, we have Vm here, we have Vm here. So effectively, the relation we're going to use is dx to the n over dx equals to n x n minus 1. So taking the derivative now becomes negative RT 1 over Vm minus B squared plus, because the minus here and then becomes plus 2A over Vm to the third. All right, so just taking the derivatives. And then we're ready to take our equation 1 and equation 2 back to this relationship and solve for our partial derivative of Vm over T at constant P. So at end, we have our, partial derivative of Vm over T at constant P times our first equation, which is this one, Vm minus B over R, and then the second term, which is this whole thing, negative RT 1 over Vm minus B plus 2A over Vm third. And this whole thing equals to negative 1. And then it becomes just a movement of terms and solving for the relationship and simplification. And what we have, solving for this, I'm just going to give you the simplified version, but it shouldn't be very hard to move the terms around. So this gives you the partial derivative of Vm over T at constant P equals to R times Vm third Vm minus B RT minus 2a times Vm minus b. And one last step is to solve for alpha, because for alpha in the front, we have a 1 over Vm term. So solving for alpha, so our alpha thus equals to 1 over Vm times partial derivative of Vm over t at constant p. And you can solve it as r Vm squared, so this Vm third becomes Vm squared, that's all. Vm minus b divided by RT Vm third minus 2a times Vm minus b. All right. It looks very complicated, but if you think about it, the math we're using is quite straightforward. The two calculus rule we use, first is the cyclic chain rule, and also just taking the derivative of a pretty straightforward function. And if you want to think about it, what is the unit of this alpha here? It is the same property. Right, so in this example, we're solving for the thermal expansivity just for a different equation of state. So your thermal expansivity will have the same unit, whichever equation of state we're using. Right, so if we think about it, what is the unit here? Now on the bottom, we see that these two are minus to each other, so we just need to focus on this first term here. And on the top, we're focusing on that top part times another Vm, right? So the Vm to the third will cancel out. R will cancel out. So the unit of alpha will still be the same as the unit of 1 over T, which is Kelvin minus. And that is the same as we solved for the ideal gas law. All right. So again, this is an example of, in thermodynamics, we have different ways to solve for the same problem. Now, in this case, you can also try solving this equation using dxy equals to x dy plus y dx. I will show how to do that on my 11 a.m. session and also record it. So if you, and also it's in the annotated note. So maybe you can like try it yourself and see if these two numbers matches with each other. Okay, do we have any questions before we move on? We're good? So again, like if you're comfortable with this kind of mass derivation, that's about this is the more complicated spectrum of math in this class. If you're comfortable with it, you should be fine with what we're gonna talk in the rest of this lecture. This class. Okay, if we don't have any questions, we're ready to move on to our next lecture, which we're moving on to chapter 2. So we'll only talk about the beginning of chapter 2 in this lecture. We'll catch up and talk about laws of thermodynamics, or the first law of thermodynamics, in our next week's lecture. So let's get started on today. Hopefully I'll be able to finish the classical mechanics and PV work. I'm not sure if I can finish heat since we only have 20 minutes left, but don't want to rush it through. So let's just start it. Okay, classical mechanics. So this, instead of a math review, this part should be more of a physics review. Again, I know physics is a part of the prerequisite, but it's good to refresh your memory on what we know about classical mechanics, or like Newton's law, right? So like thermodynamics, classical mechanics take care of our macroscopic world. Or when we're saying classical mechanics, it describes laws of, it is laws of motions of macroscopic bodies whose speeds are small compared with the speed of light, right? So this tells you what kind of problems are suitable for classical mechanics. For example, like non-macroscopic objects like an electron or a hydrogen atom. So these are too small to be considered in the macroscopic world. They need to be treated using quantum mechanics. Or something moving super fast, right? Very high speed objects that's not uncomparable with the speed of light. So these will take care using the relativistic mechanics. So our deal will be like large bodies of objects, something you can like actually touch, and they're relatively moving slowly comparing to the speed of light. So in classical mechanics, well, the most famous one is Newton's law, right? You have force, which is a vector, that's equals to mass times acceleration, which is also a vector. You have velocity, which describes the change of distance over time. And acceleration is defined as the second derivative of change of the movement over time. And we have work. So when we say work, we have the change of work, or dW, equals to fx dx, so that's one-dimensional work. What it tells us is when a force acts on a body while the body undergoes an infinitesimal displacement of dx in the x direction. So that's our work, that's definition of work. If we want to get the work from this equation here, we need to take the integral, which gives us, well, the integral of dw gives us work from x1 to x2 fx dx, right? So the unit of your work is obviously Newton times meter or joule. So this part is all very straightforward, right? And then we have our energy. So since our work has a unit of joule, it's somehow related to energy, or vice versa. But it's definitely, work is related to energy, but how exactly is it related? So that goes to our mechanical energy, which is the work energy theorem, focusing on the kinetic energy. So work is more directly related to kinetic energy. Or the other way to put it, in the work energy theorem, we have the work done on the particle by the force acting on it equals to the change in kinetic energy of the particle. Well, I'll highlight this part, the change in kinetic energy, and we'll come back to it later on. So I'll do a very quick derivation with you because this is a quick review on your physics. So let's just set F as the force acting on the object or particle of interest. Right, so depending on the direction, we can write our total work equals to the three directions adding up to each other. So x1 to x2, fx dx plus y1, y2, fy, dy, and z1, z2, fz, dc. You can use other coordinates other than Cartesian coordinates, but we're just going to stay with Cartesian coordinates for simplicity. Now, what we know in Newton's law is that fx equals to max, right? So F equals to ma along the direction of x. So in this case, we can rewrite that as m equals to change of velocity at direction x over t, and that equals to m times dvx dx dx dt. So this one just using calculus. We're just manually add this dx here in between. And then we can solve to equal to m vx dvx dx, like this one. the change of x over t just equals to velocity, Vx. Right, so this just simplified to be Vx dx. Right, so plug this one back, because fx is here, or like fy and fz. We can go back and rewrite our work. Equals to the velocity Vx1, Vx2, m, Vx. Now this one is dx, so we can have mvx dvx. Yes.
The interval supposed to be x1 and x instead of dx1?
This one is actually Vx1, Vx2. So we'll plug this one in, so the dx and dx will cancel out, and then what is left is dvx. Right, so we'll plug this entire thing into here. So dx and dx will cancel out. All right? Let me just not skipping any steps. So if we're focusing on this term here, this just becomes fx, we're just writing it in there. That's mvx dvx dx dx. And these cancel out. And thus our work becomes Vx1, Vx2, mvx dvx, and the same for other directions. All right, so taking that integral out, now this one is a definite integral we can solve for. Mass is not dependent on your Vx. And then you can solve it as 1 over 2 m Vx2 squared minus Vx1 squared plus 1/2 m Vy2 squared minus Vy1 squared, etc., etc. And later on, after simplification, we get work equals to 1/2 m Vx2 squared plus Vy2 squared plus Vz2 squared minus 1 over half m Vx1 squared plus Vy1 squared plus Vz1 squared. Or the other way to put it is we use the work energy theorem to define the kinetic energy, right? So that's the obvious expression of our kinetic energy. K equals to 1 over 2 mv squared. Or our work equals to K2 minus K1. So that's our work energy theorem. Right, so again, going back to our original definition, the work done on a particle by the force acting on it, so that's this work, equals to the change in the kinetic energy of the particle. One thing we want to highlight is that the work is only a meaningful term when it is describing the change of kinetic energy. So that's different from just saying like kinetic energy or potential energy, right? So for kinetic energy or potential energy, you have a object and you can just describing it using, like say this is a state, this is the amount of kinetic energy this particle have at the current moment. But work is not something you can define by only looking at the object itself without any change. All right, it's only defined by the change in kinetic energy, even we're looking at the work theorem perspective. All right, so work is related to change. We'll come back to see why it is important in a minute or so. Another part of the mechanical energy is the potential energy. So this part is the kinetic energy. And then we also have the potential energy. So in this case, the potential energy, let's say a capital V, I know it's the same V as volume, but unfortunately, we only have 26 alphabetics. So the capital V potential energy as a function of x, y, and z is defined to be the partial derivative of V in direction x, well, gives you the force acting in that negative of the force acting in that direction, etc. And in classical mechanics, we have conservation of mechanical energy. So that means the total energy, the total mechanical energy, which is the sum of your kinetic energy and potential energy, that's always conserved. So that's a quick review. And then let's move on to talk about PV work. And by the way, there's a sample problem here that somehow went missing for some reason. So this one should be problem 2.6. It's just a change of unit, and just get familiar with different unit people use. Nevertheless, so moving on to talk about PV work, or back to what we were saying, we will end on why it is important to recognize that work is something that describing change. So before we say that, we want to define what is reversible versus irreversible. So you will hear the term reversible process very often in this class. All right, so it is important to know what is the definition of a reversible process or a reversible system. Now, the reversible system is a system that is always infinitesimally close to equilibrium. Any infinitesimal change in the conditions, meaning we change the pressure a little bit, we change the volume a little bit. So any infinitesimal change in conditions will restore both the system and the surrounding to their initial state. All right, so they're super close to equilibrium, but not at equilibrium yet. So only very slow processes can take place. Now, in this case, let's just look at work. Right, so this is a stereotypical PV work diagram you will see. Again, we have Fx and dx moving in the same direction. What we're having is a positive work is done on the system. Imagine these are the gas that's being compressed by a external force, right? And since we're compressing it, we're moving Fx in the same direction as x. We're doing positive work on the system. The volume of the system will decrease, or this dx will become, it's going in the same direction as our force. Now, remember what we have is the dw equals to fx dx. Now, in this process, we have pressure, px, equals to Fx divided by area, and then the work equals to Px area dx. Right, so Fx becomes A times Px. And the change of volume, so this one is volume, equals to negative A dx. So when x is moving to the right, our volume is decreasing. So there's a negative sign in front of our change of volume here. And at the end of the day, we have a pretty straightforward derivation. So dw reversible equals to negative px dv. We're talking about closed system and reversible processes. So whenever we say it's a reversible process, just keep in mind, whenever we see something like super slow, it's pretty much hinting like we have a reversible process. So with this in hand, we can actually do the integral and solve for the total work done on the system, right? So we will be using this very often. That is, taking the integral of the W reversible, taking the integral between V1 to V2 PdV. That gives you the total work done on the system. So remember, we want to end at what exactly do we say when we say work is a path-dependent function? We're talking about work is only defined when we know how it gets between A to B. I'm going to show you two very simple processes. Imagine a closed system containing just ideal gases. So we have like PV equals nRT, and you can actually solve for numbers because it's an ideal gas. Now we're thinking about the initial state as P1, V1, and our final state as P2, V2. Right, so the initial and final are the same. And now let's consider two different processes. First one is a isochoric process followed by a isobaric process. And let's say like our P1 larger than P2, V1 larger than V2. Just randomly set it. You can set it differently. So when we plot this first process, which is isochoric followed by isobaric, we start from P1, V1, we end in P2, V2. And this is our typical PV diagram. So if you think about it, we have isochoric. So we're keeping the volume constant while changing the pressure. So what that means is our first step is an isochoric process. We're keeping the volume the same as V1, and then we're changing the pressure to V2. Right? And in this process, taking the area below the curve gives us what is V, what is work, what is W in this case. Now, if we look at the area below the curve, that's about this big. All right. The same processes, if we're thinking about the same initial and final state, which is V1, V2, and P1, P2, V2, and which start from P1, V1 and ends in P2, V2. And now we're talking about a different process. Just removing all these lines telling us about the process. And talking about a isobaric process followed by isochoric. So isobaric process tells us we keep P as not changed as P1, right? We keep P1 in our first step. And then we have our second step, which is the isochoric process of keeping the volume the same. Now, in the second path, which is a isobaric followed by an isochoric processes, the volume between these curves now becomes this big. It is a much bigger work needed if we're doing the work at a isobaric followed by isochoric process. All right. You can also think about other ways to do this kind of transformation, but just keep in mind we cannot calculate the work that's being done under this curve. Well, we cannot calculate the work that's being done, knowing only the initial spot and the final spot. We must know how the process is taking place. We must define the path, and that is why work is called a line integral. It's a path dependent. So in our next lecture, we'll look at another path-dependent property, which is heat. And then taking them together, we'll see how they work together to define new state functions in thermodynamics. All right? All right, I'll upload our recording soon, and let me know if you have any questions later. And keep in mind, we have homework due and syllabus quiz due, well, Sunday and today.